Today we're going to actually use some of the pieces that we learned about in the actor critic and value functions lectures and bring things back to policy gradient and see how we can reinterpret the policy gradient as a kind of policy iteration and how this gives rise both to a deeper theoretical understanding of why policy gradient works and also a few more advanced algorithms. So first, a few logistical notes. Homework 2 is due today at midnight, so hopefully all of you are well on your way to finishing that. So please don't be late, and please remember that you have at most 5 late days cumulative over the entire course, so if you have to turn something late, make sure that over all of your assignments it doesn't add up to more than 5. Homework 3 is going to come out this week, probably tomorrow or maybe on Wednesday. Homework 3 is going to be a bit longer than the others, and also for homework 3 you'll be implementing Q-learning, including Q-learning from images, and that takes quite a bit longer to run. So do make sure that you start early so that you have time to actually run your Q-learning experiments. We do have it set up so that you can debug your Q-learning implementation on some smaller, simpler problems, but we will want you to run it from image observations ultimately, and that will take like about a day to run, so make sure you leave plenty of time for that. So start early. All right, today's lecture. So today we're going to learn about why policy gradient works. So we saw kind of an intuitive interpretation of why policy gradient works when we started this discussion, back when we talked about how it's essentially gradient descent. But today we'll learn about kind of a deeper explanation for why we might expect policy gradient to work well. We'll learn that policy gradient can be viewed as a type of policy iteration. And we'll see how we can frame, how we can actually derive policy gradient from a constrained optimization view of policy iteration. And then from there, we'll actually end up deriving a natural gradient formulation of policy gradient. And from natural gradients, we can get to trust region policy gradient methods, which are actually very effective policy gradient methods to use in practice. So we'll kind of have the natural gradient, the more practical side of things in the second half of the lecture, and the first half will focus more on the theory behind policy gradients and policy iteration. So the goals for today will be to understand the policy iteration view of policy gradients, understand how we can analyze the amount of improvement that you can get with every gradient step in policy gradient, and understand what natural gradient does and how we can use it. All right, so first, since it's been a while since we talked about policy gradients, let me briefly recap the central idea. So this is the most basic policy gradient algorithm that we learned about, the reinforce algorithm. It consists of 3 steps. In step 1, you sample some trajectories by running your policy in the environment. In step 2, you estimate a policy gradient, which you do by using samples, and you average together the sums over time of the grad log pi's and the total rewards to go. And then step 3 is you simply apply the policy gradient, which corresponds to you doing gradient ascent with some learning rate alpha. So in our favorite diagram, we can imagine that regular policy gradient simply sums together the rewards for this green box and applies the policy gradient for the blue box. And we saw, of course, that the policy gradient can be equivalently written as a sum over all the time steps in all of your samples of grad log pi at that time step in that sample times this q hat thing, which we refer to as the reward to go. And the q hat can be calculated in a variety of different ways. You could simply sum together the rewards like we did in the first policy gradient lecture, so that's what we're doing up here. Or you could use some function approximation like we did in the actor-critic algorithms. So there are a variety of different ways to estimate this q hat to give you an estimate of the reward to go after taking action AIT in state SIT. Okay, so that's the recap of policy gradient. So now, why does policy gradient work? To think about this, let's think of a very high-level schematic view of policy gradient. So if we're doing some kind of function approximation, or if we're summing together the r's, it doesn't really matter. Somehow we're estimating advantages. You can use q values too, but we saw how if you use a baseline, they really turn into advantages. So you're somehow estimating these a hats. So you can think of the algorithm at a very high level as step 1, estimate a hat for your current policy pi. Step 2, somehow use a hat to get a better policy pi prime. And in particular, you would, in policy gradient, get the pi prime by using your a hat inside this gradient estimator, applying the gradient via the gradient ascent rule, and using that to get a new policy pi prime. And then repeat the process. So that's a very high-level kind of schematic view of policy gradient. Now, this should look kind of familiar to some of you. We saw something a little bit like this in the lecture on actor-critic algorithms and in the lecture on value function methods. This general scheme, step one, evaluate how good your policy is. That's what A hat is. A hat tells you how good different actions are for your current policy. And step two, use your estimate of how good the policy is to make it better. That's the basic recipe behind a policy iteration method. So the policy iterations outline that we saw before looks like this. Evaluate the advantage of your policy, which you could do by estimating a value function or estimating a Q function, whatever. Somehow you get advantages out of it. And then use those advantages to get a better policy. And when we talked about, for example, Q-learning methods, we saw how we can get a better policy simply by taking the argmax. When we had actor-critic, we had to use a gradient. So these two things are actually very similar. And indeed, we can actually frame policy gradient as a type of policy iteration. Before we go into that, what are kind of the most obvious differences? Like, how is the policy gradient scheme, where we use this gradient to improve the policy, on the surface, how does it seem different from policy iteration? Or do you guys just think they're like exactly the same? Any thoughts? For example, let's take the Q-learning style scheme where the way that you would choose pi is by taking the argmax.
Yeah, we represent the policy explicitly.
Okay, so one thing is that we're representing the policy explicitly. Another thing is that, well, this is a gradient step. A gradient step doesn't really necessarily by itself maximize something. If you take many gradient steps, maybe you get to some optimum. But if you take one gradient step, that isn't necessarily maximizing some objective. So we could have a full policy iteration procedure where we estimate A and then we optimize against data convergence and get maybe a much better pi. We'll actually see how policy gradient, when we use the policy gradient to improve the policy, does indeed optimize an objective, just a different objective. It actually optimizes a constrained objective. And we'll see that in the second half of the lecture. Okay, so let's try to work a little bit on this idea of deriving how policy gradient is in fact doing policy iteration. So here's how we're going to start. We're going to start by analyzing the policy improvement objective. So remember from before, J of theta, I use J of theta to denote the expected total reward of a policy. So this is the definition of J of theta. It's the reinforcement learning objective. And I've stuck a discount in there since we always like to have discounts. This is a improvement objective. So it's the difference between the expected reward for a new parameter vector theta prime and your old parameter vector theta. And we'll see why we're doing policy improvement in a second. And what I'm going to try to show as a starting point for this equivalence between policy gradient and policy iteration is that policy improvement is equal to the expected value of the advantage of your old policy pi theta under the trajectory distribution of your new policy theta prime. Why is this interesting? This is interesting to us because this thing is what you would expect to see in a policy iteration algorithm. In a policy iteration algorithm, you would expect to see the following structure. Estimate the advantage of your current policy, and then maximize that advantage with respect to the new policy. So the structure that you would expect in a policy iteration algorithm is step one, figure out what A pi theta is. Step two, maximize this quantity. Basically, get the new policy to take the actions for which A pi theta is big. So all policy iteration methods do some variant of this. If we can show that J theta prime minus J theta is equal to the policy improvement objective in policy iteration, then we're on our way to show an equivalence between policy gradient and policy iteration, because when we take the gradient of this thing, if the gradient of this thing is in fact the gradient of this thing, that means that policy gradient at least moves in the direction of improving the same thing as the policy improvement step in policy iteration. Okay. Does anybody have any questions about why we're trying to do this? Yes?
We are optimizing with respect to theta prime.
Yes. So theta prime is what we want. Theta is our old parameter vector. Okay, good. So now let's try to see if we can prove that this thing is equal to this thing. So the first thing we're going to do is we're going to take j theta and we're going to substitute in the definition for the RL objective in terms of value functions. So the RL objective is the expectation of the total reward under your trajectory distribution. But remember that the value function is the expectation of rewards you'll get starting from a particular state. So that means that the entire RL objective, the entire j theta, can be equivalently written as an expectation under the initial state distribution. And I apologize, there's a typo. This should be S0 distributing according to P of S0, not P of S1. So expectation under S0 of the value function at S0. Which value function? The value function for pi theta. So that we get that from just the definition of value functions and from the definition of the RL objective. Now, of course, an expectation with respect to S0 can be equivalently written as an expectation with respect to any trajectory distribution, because any trajectory distribution for any policy has P of S0 as its initial state marginal. So I can change that first line to write the expectation with respect to the trajectory distribution for any policy, and the one that I will choose is the trajectory distribution for theta prime. But they're all the same. So this is also equal to, if I were to use P of theta, P of whatever, for any policy, every trajectory distribution will have the same first state marginal, because all policies start off in the same states. So that's why I'm allowed to make that substitution right there. But now that I've made that substitution, I'm going to do this. I'm going to take the thing inside of that expectation with respect to P theta prime of tau, and I'm going to add at every time step. At every time step after 0, I will add v pi theta st, and I will subtract v pi theta st. So if you add a number and subtract a number, that equals to 0. And I will add and subtract that v at every single time step except for the very first one. So that's why I have one sum from t equals 0 to infinity, and then I'm subtracting everything from t equals 1 to infinity. Right? So if you subtract everything from 1 to infinity, the only thing you're left with is the thing at time step 0, which is what I had here before. So I'm allowed to do this because you can always add and subtract the same number, because that adds up to 0. Yes?
Do those converge, like, at the sum?
Do these sums converge? These sums converge because I have a discount. So as the t's increase, for any gamma less than 1, those multipliers will go to 0. So those are, in fact, convergent sums for a discount less than 1. Any other questions? OK. So now let's group the terms a little bit. So what I've done here is I've switched this minus to a plus. So the whole expectation used to be a minus before, now it's a plus. So the two values flip. So then you get the ones from 1 to infinity on here, the ones from 0 to infinity on that side. So then you can write it as a sum of the differences between the values, and one of them has a gamma in front of it. Right? So the one with the gamma in front, that comes from here. The one without the gamma, that comes from here. So I've just rearranged the terms. OK? So far, so good. Now I'm going to make one more substitution. I'm going to take the j theta prime, which I haven't touched before, and I'm going to just directly substitute in the definition of the reinforcement learning objective. So I'm just going to directly substitute in the sum of rewards. I'm allowed to do that. That's literally the definition of j theta prime. And of course, because it's j theta prime, its expectation is also under p theta prime. So the expectations are with respect to the same distributions. So now I can merge these two expectations by linearity of expectation. And I can see everything here is multiplied by gamma to the t, gamma to the t. So I'm going to put this r inside of the sum. And that gives me the sum of the expectation with respect to p theta prime of gamma to the t times r plus next v times gamma minus current v. And what is this thing inside the parentheses? Anybody want to volunteer a guess? R plus next v minus... It's the advantage, yeah. So the advantage is defined as the q value minus the value, and the q value is just this bit. So that means that this is the advantage. So now I've proven my claim that the difference between the expected return of the new parameter vector minus the previous one is just the expectation of the advantages of the previous policy in expectation under the trajectory distribution of the new policy. OK, any questions about this proof? Okay, so now let's continue down our journey. Let's try to see if we can actually optimize this. We're not quite there yet because we still have this expectation under p theta prime. So let's turn this into something that looks a little bit more like policy gradient. So far we have the advantage under pi theta and an expectation under pi theta prime. That's no good because it's very difficult to calculate a gradient for that without generating additional samples from pi theta prime. So here's what we can do. We can write it out in the other form that we saw where we use marginals. So if you have the sum of an expectation under some joint and the thing inside the sum factorizes, we can equivalently take the sum outside and say that it's the sum of the expectation with respect to the state marginal, p theta prime, of the action with respect to pi theta prime of the advantage. So I've just pushed the sum out of the expectation. And now I'm going to apply my importance sampling trick from before. So if you guys remember the importance sampled policy gradient lectures from the beginning of the course, we'll just use exactly that same trick in order to make this expectation be with respect to pi theta instead of pi theta prime. Remember, my samples come from pi theta. They don't come from pi theta prime. So if I put in the importance weights, now I can at least make this inner expectation be with respect to my old policy pi theta, but I have to put in those importance weights. Okay, so that's one thing out of the way. Am I done yet? What's the problem? I still have a problem, a pretty big one. What's preventing me from optimizing this objective? If I have samples from pi theta. Yes? I still have theta prime in the outer expectation, yeah. So this thing is preventing me from using samples from pi theta to optimize this because this says I need to calculate an expectation with respect to p theta prime of st, and I don't have p theta prime of st. I just have samples from pi theta. So I'm not done yet. So what do? We have the wrong states. Well, can we just ignore the problem? Can we just use pi theta of st instead of pi theta prime of st? Because if we just replace this with pi theta, then theta prime only appears right there. And we know how to deal with that. That just turns into our favorite grad log pi term. So if we could just cover that bit up somehow, then we would be all set. Okay, so can we just ignore this distribution mismatch? Meaning, can we take our actual objective, and keep in mind, we haven't made any approximations so far. We're just writing out something that is exactly equal to the difference of returns. If we could just write it like this, with a p theta there, and then theta prime would only be in one spot, where it's easy to manage. There, it's easy to calculate the gradient. If only this were true, then we would be all set. So is this at least approximately true, at least sometimes, at least on a good day? Why do we want it to be true? Well, if this were all true, then let's say that this whole thing, let's call it a bar of theta prime. If this were true, then that would mean that the difference between j theta prime and j theta is approximately equal to a bar of theta prime, and a bar of theta prime is something whose gradients we can calculate with respect to theta prime without generating any new samples, which means that we could take its argmax, we could figure out the theta prime that maximizes that a bar just by running a regular gradient-based optimization without interacting with the environment at all, without generating any new samples, and without even calculating any new advantage functions. So if only that right-hand side was approximately true to the left-hand side, we could implement this policy iteration thing. And that would basically be the policy iteration step, the improvement step in policy iteration. So we really, really want that to be true. So is it true, and when is it true? My claim is going to be that p theta of st is close to p theta prime of st when pi theta is close to pi theta prime. That sounds a little silly at first. If I do the same thing, I end up in the same states. That's kind of almost seems obvious. But if we want to actually derive convergent, well-defined algorithms, unlike all this Q-learning business we saw before, we want to actually prove that this is true rather than merely asserting it. And in particular, it's not actually quite as trivial as it might at first seem, because while it's obvious that the state marginals of two policies are the same if those policies are actually the same, once the policies begin being different from each other, it's not at all obvious that they land in the same state. So if you imagine the car driving at the edge of a cliff, well, a small difference in action might lead to a very large difference in states potentially. So we need to actually prove that when pi theta and pi theta prime are close together, p theta st and p theta prime of st are in fact also close together. And in order to do that, we need to define what close together means and all this other stuff. So let's work on that a little bit. Let's bound the distributional change. So here's our claim. P theta of st is close to p theta prime of st when the policies are close. So we'll start with a simple case, just to practice, and then we'll go to a more advanced case. So in the simple case, we'll assume that pi theta is a deterministic policy. It's not, but we're going to assume that anyway because that makes the derivation a lot easier. On the next slide, we will relax this assumption. So if pi theta is a deterministic policy, we can equivalently write it as a function, at equals pi theta of st. And then we can define the following notion of close. We can say that some stochastic policy, pi theta prime, is close to the deterministic policy pi theta if the probability of pi theta prime taking an action that is different than the deterministic pi theta action is less than or equal to epsilon. I'll come back to that shortly. Where have you guys seen that before? You have one policy that deterministically takes some action. You have another one that has a bounded probability of taking a different action. Where did we see that before?
Imitation learning?
Imitation learning, yeah. So we saw that in the beginning of the course when we learned about how to derive bounds for imitation learning. In imitation learning, we used this definition to define what it meant for an imitation policy to be close to the expert. Now we're using it to define what it means for the next policy pi theta prime to be close to the previous policy pi theta, with this weird constraint that pi theta has to be deterministic, which we'll get rid of on the next slide. So back from our imitation learning lecture, we had this relationship. Raise your hand if you remember this. Raise your hand if you don't remember it. Raise your hand if you're not responding because you're shy or don't want to raise your hand. Okay, so roughly equal proportion of the class. Let me briefly summarize what's going on here. So if we have the bound that pi theta prime makes a mistake with probability less than or equal to epsilon, we can turn that into a bound on the difference between pi theta st and pi theta prime of st. And the way we do that is by writing out pi theta prime of st as the sum of two terms. The first term is equal to pi theta of st, and that comes from the fact that with some probability, your new policy pi theta prime might do exactly the same thing as pi theta. What is that probability? Well, it's 1 minus epsilon at every time step. So if we're talking about st, that means that 1 minus epsilon to the power t is the proportion of the probability mass that ends up from the policy doing exactly the same thing. So at every single time step, 1 minus epsilon is the probability that pi theta prime does the same thing as pi theta, which means that after t of those steps, you have a coefficient of 1 minus epsilon to the power t in front. So that's this term. This is basically the portion of your state probability mass that is exactly the same as your old policy. And then 1 minus that is just everything else. We don't know what that everything else is. It could be anything. The car could have gone off the cliff. So this is the probability we made no mistake, and this is some other distribution that we don't know anything about. So we saw that before when we studied the dagger setting in imitation learning. So that means that we can bound the total variation divergence between p theta prime and p theta as basically the coefficient in front of this term times the difference between p mistake and p theta. Does everybody remember what total variation divergence is? Please raise your hand if you remember what total variation divergence is. Raise your hand if you do not remember total variation divergence. Okay. Let me summarize it on the board. Okay, when I write this, it's basically the most obvious notion of a metric over distributions you could think of. It's the sum over all possible values that this could take on of the absolute value between their probabilities. Right? So this is basically just the distance between the probability distributions, literally using absolute values. So simply by using this equation up top, I can say that the difference between p theta prime and p theta is equal to this. How do I do that? Well, I simply substitute this stuff in place for p theta prime and then group the terms together. Does anybody want me to go through that? Raise your hand if you want me to go through that derivation in detail. OK, nobody wants to see that. Good. So it's exactly the same as it was before. All right. Now, we can bound this by 2 times the coefficient. Why can we bound it by 2? We're basically replacing this term with 2. And the reason we can bound it by 2 is when you have the sum of the absolute values of the differences between two distributions, we know that all probabilities are greater than or equal to 0 and less than or equal to 1, which means that, and they sum to 1, which means that when you sum over their absolute value differences, the maximum difference between two distributions can add up to at most 2. Right, because if the distributions are as different as they can be, that maybe one of them is big in one place, the other is big in the other place, their probability mass is at most 1. So plus 1, absolute value of minus 1, adds up to at most 2. So that means that I can always bound any total variation divergence by 2, and therefore I can get this bound. Now there's this useful identity, which we saw before when we talked about imitation learning. That simply allows us to get rid of this annoying exponential term. So if epsilon is between 0 and 1, then 1 minus epsilon to the t is greater than or equal to 1 minus epsilon times t. So we substitute that in there, and we get a bound of 2 times epsilon times t. OK, so after all of these contortions, what have we actually arrived at? We've arrived at the observation that the total variation divergence between the state marginals at time step t is at most 2 times t times epsilon, which is your probability of making a mistake. It's not a great bound because it gets bigger and bigger as epsilon gets bigger, but it's still a bound. And for a small enough epsilon, the state distributions will be close enough together. OK, now this is for this weird case where pi theta is a deterministic policy. If you're doing policy grading, pi theta is not a deterministic policy. It's going to be a stochastic policy pretty much always. So what we would really like is we would like to derive the general case where pi theta is an arbitrary distribution. Now, in this case, we have to define a new notion of close. Before we said that two policies are close if one of them takes a different action with some bounded probability, but now they're both stochastic, so what does that mean? Well, we're going to define close, again, in terms of total variation divergence. We'll say pi theta prime is close to pi theta if the sum of the absolute values of the differences of their probabilities is bounded by epsilon. And actually, if you look at this definition, if you pretend for a minute that pi theta is deterministic, that actually just means that it has probability of 1 for a particular action and 0 for everything else. This definition in that case is actually exactly the same as the one on the previous slide. But this definition is more general because it will also apply to stochastic policies pi theta. All right. So if we want to use this definition and still derive a bound like we did on the previous slide, we need a very useful lemma. This is going to be a little weird, but it's kind of intuitive. At least for me it is. Hopefully it is for you too. Here's the useful lemma. If you have two distributions, we'll call them px and py, and the total variation divergence between px and py is equal to epsilon, then you can construct a joint distribution p of x comma y such that px is the marginal with respect to the first argument and py is the marginal with respect to the second argument. Take a moment to think about what that means. So you have one distribution px, another distribution py. There are many ways to construct their joint, but the claim is that there exists one way of constructing their joint such that the probability of x and y being equal is epsilon. So that means that if you have a distribution px and a distribution py, their total variation divergence is epsilon, you can construct a joint where they will agree with probability epsilon. This is kind of the generalization of the notion that the two distributions take on the same, that samples from the two distributions take on the same value. So if we say that our px is our pi theta and our py is our pi theta prime, then from this it follows that pi theta prime takes a different action than pi theta with probability at most epsilon if we sort of align them properly. Align them properly meaning use the same random numbers. This is a slightly hand-wavy explanation of this idea. You can find a much more detailed derivation of it in this paper called Trust Region Policy Optimization. But the high-level intuition is that these two policies, if their total variation divergence is epsilon, then they can be said to take the same action randomly with probability epsilon, which is kind of the generalization of the notion of a mistake that we had from the previous slide. So before we said that pi theta prime makes a mistake with probability at most epsilon. Here, same exact thing. Pi theta prime makes a quote-unquote mistake with probability at most epsilon. But now, since pi theta is itself stochastic, we need this more complicated technical lemma to make that actually make sense. But once we have this lemma, once we basically can say that pi theta prime will make a mistake with probability of at most epsilon, then we can directly reuse everything that we had on the previous slide, simply plug it right back in, say that, well, if they'll take the same action with probability at least epsilon, different action with probability at most epsilon, that means that, again, we have the difference between p theta prime of st and p theta is 1 minus epsilon to the t times the difference between p mistake and p theta. So that's exactly the same as on the previous slide. And we bound it just like we did before by 2 times epsilon to the t. So long story short, using this very useful lemma, we can do exactly the same thing that we did before, except that now pi theta is stochastic, and instead of assuming that we take a different action with probability epsilon, we assume that we have a bounded total variation divergence. Yes?
So I'm kind of confused, and this might just be like a dumb question, but so on the useful lemma, the probability x equals y equals epsilon, why is that not like not equals y and then disagrees in the next slide? Like I don't understand how you're going from agreement to the fact that they take different actions with probability of epsilon.
Oh, it's because this should be 1 minus epsilon. Thank you. Yeah, so just to make sure that everybody caught that, thank you. Let me write out what it should be. So p of x equals y equals 1 minus epsilon, this. So that line, the first line of the useful lemma, should state this. Thank you for catching that. All right. So here's what we have so far. We know that if pi theta prime is close to pi theta, close meaning that their total variation divergence is bounded by epsilon, then their state marginals are bounded by 2 times epsilon times t. So we've gone from a similarity on policies to a similarity on their state marginals. So how does this help us? How does this help us show that the left-hand side of that giant equation from before is approximately equal to the right-hand side? So let's derive sort of a general version of this, and then we'll substitute that into our original equation. So if you have an expectation of some function, let's say that function is f, we can write that expectation as the sum over all states of p theta prime of s times f of s. And now our goal will be to rewrite this in terms of an expectation under p theta by exploiting this relationship and some error terms. And those error terms need to be small as epsilon becomes small. So here is the actual relationship we're going to show, and I will derive this on the board. All right, so we start off with a sum over st
of p theta prime of st f of st. Okay?
That's just the left-hand side of this.
And now this is equal to the sum over st of p theta prime plus p theta minus p theta. All right, so this is everyone's favorite trick. Just add something and then subtract it back out again. And this is multiplied by f of st. Okay? So now we're going to group these terms. We're going to rewrite this as being equal. So I'm just going to rearrange the terms and group them to p theta of st times f of st. So I'll just do a little bit of a distribution. So I'll distribute this inside. Plus, and here I'm going to put some parentheses around it, p theta prime of st minus p theta of st times f of st. Okay? So I just put this guy here, this guy here, this guy here. All right? Just distributed and rearranged terms. Now, we know that the absolute value of a number is greater than or equal to that number. So that means that we can change these parentheses to an absolute value and just change this to this, right? You can always do that. And now we're almost there. So now we have this first term, which is an expectation of f of st under p theta of st. And then we have this other term, which looks like a little bit of a mess. Now, we'll take this f of st and we'll replace it with something that doesn't depend on st, specifically the largest value that it takes on. So we'll replace it with a max. Oh, you guys probably can't see it down here. We'll replace it with a max over st of f of st. So we'll replace that. So now for this other term, we have an absolute value that doesn't depend on st, and we have this max that doesn't depend on st. So these things are now both constants. And we're just left with the first term, which is an expectation with respect to p theta, and a second term that is a constant. And then we can substitute this in, the 2 epsilon t, in place of the total variation divergence between the state marginals, and get this bound. All right? So now we know that for any function f of st, we can bound its expectation under p theta prime by its expectation under p theta minus 2 epsilon t times the maximum value that that function takes on. And this is actually useful to us because if epsilon is very, very small, this second term might be negligible. All right, so now what are we going to use for f? Well, we're just going to use the thing inside that expectation. So we have this complicated thing inside the expectation. That's going to be our f. So we'll just plug that in. And when we plug it in, here's the bound we get. We get this thing. Now the expectation is under p theta, which is what we wanted. But then we have our error terms. And the error terms are going to be, over all the time steps, 2 times epsilon times t times a constant. The constant accounts for this max. Let's think about the constant for a second. F is this thing inside the expectation. It's the expectation of the actions, of the importance weights times the advantages. Now, everything here sums to 1 except for the advantages. So you can basically say that this constant, it's going to be essentially the largest advantage value you can get. What's the largest advantage value you can get? Well, it's just the largest reward you can get times the number of time steps remaining. So this constant is going to be on the order of t times r max for a finite horizon problem. For an infinite horizon problem, it's going to be on the order of the sum of discounted rewards. And to calculate the sum of discounted rewards, we're going to use our knowledge of convergent series. So sum over t of r max times gamma to the t. That's what we want. The r max can go outside the sum. So that's just r max times sum over t of gamma to the t. And there's actually a very convenient formula for doing this. And the formula gives us r max divided by 1 minus gamma. So this is a formula you can look up in a textbook if you'd like. If you have a sum of gamma to the t, it's just 1 over 1 minus gamma. So in the discounted case, it's on the order of R max divided by 1 minus gamma. So this is the discounted setting. This is the undiscounted setting. It's a big constant, but it's still multiplied by epsilon. So if epsilon is very, very small, this might be a reasonably a manageable term. OK, so this gives us a bound. What does this bound mean? It means that if we optimize this thing, the expectation under p theta, and we improve the objective by more than this constant, then we've improved our original objective over here, which, as we saw before, is equal to the difference between j theta prime and j theta. So that means that if we improve this bottom objective by more than the constant, we will have made our policy better. And that's very good because we want to make our policy better. OK, does anybody have any questions about the bound that we've derived here? Yes?
When you derived it on the board, you had a less than or equal to and a plus. Yeah, you sort of erased it.
The thing I erased, OK.
But up on the screen, it's greater than or equal to.
OK, so are you talking about this or the next slide? Next slide.
So you separated, you added and you subtracted p theta of s.
When I separated, you mean this part?
Yeah. So yeah, that minus sign, and then and equality is like greater than or equal to. But on the board, you had it as a less.
Oh, but it's an absolute value. So you can flip the absolute value whichever way you want. Right, because absolute value of p theta minus p theta prime is the same. Any other questions about this? Yes?
How do we determine epsilon? I mean, it seems if we don't know what epsilon is, then...
Yeah. So the question was, how do you determine epsilon? It seems like if you don't know what epsilon is, then how do you know this makes any sense? So that's a very good question. And what we're going to do in actually pretty much the remainder of the lecture is figure out how to optimize pi theta prime so that epsilon is not too big. Because if we can ensure that theta prime doesn't change too much away from theta, then we know that epsilon will not get too big. Any other question?
One more quick.
Yes?
So initially you did some math to expand this equation, and you had one expectation over phi prime or theta prime, and you expanded out and you got two, and then you did
These two expectations.
Yeah, but if we have this proof that shows that the expectations with respect to theta prime is close to the expectations with respect to theta, then why did we need to expand it out in the first place? Couldn't we have just left it as one?
Right, so you could actually go through a derivation similar to this at the level of trajectory expectations. I think this one is a little bit simpler, but you can try going through the other one. It'll actually work as well. All right, so where are we at so far? Where we're at so far is that if we can maximize this thing with respect to theta prime, we'll get a better policy, but only if pi theta prime doesn't get too far away from pi theta. So we quantified too far away in terms of total variation divergence, so that suggests that we can try to solve a constrained optimization problem. We can maximize that objective with respect to theta prime, subject to a constraint that the total variation divergence between pi theta prime and pi theta is less than or equal to epsilon. And if we choose epsilon to be small enough, then we can get an improvement. If we choose epsilon to be small enough, then optimizing this will actually improve j theta prime minus j theta. So we're going to take a little break right now, and then after the break, we'll talk about how we can actually solve that kind of constrained optimization, at least approximately, and actually recover something that looks like policy gradient. So we'll be back at 10, let's say 58, so in 3 minutes.
Well, I threw up, I have 4 cores, so 8 threads. So I opened 8 terminals, and I'm running each, like, you know how we had to run those 9 of those? I ran 8 of those 9 in one shot. So my computer has 8 different terminals running different Python iterations to train all of the different ones at the same time. And it has depleted half of my battery since we came into this class. Well, I mean, yes. Like, if I was actually writing it appropriately, like, I've written parallel code, it would be one terminal that would throw out all of them itself and run them. And then, but then in this case, I literally didn't actually bother to write the code to parallelize it. I literally independently ran the script in 8 different terminals. So it's manually multiprocessing.
You're gonna burn that table, bro.
Oh yeah, it's getting hot.
I did the 170 project, and I felt like I actually had to put my computer back. So I put it up against the window and just pulled it outside.
Oh yeah, no, I'm at 85% CPU usage and have been there for like a good 20 minutes. Oh no, yeah, because it's going to save me time because each one of these processes can only run up to 100% of its like CPU that it's running that process on it, and so all the threads are running 100% of their CPU that they're allocated.
Oh, I see. Okay.
So each one of them exists in a separate thread on its own core, and so, well, I mean it's multi-threaded, so that means that it's fake core.
Yeah.
But yeah, so each one of them exists on basically half the core. And voila. Now all of them are training simultaneously.
Is the code set to work automatically attached to something?
All right, let's continue. All right, so before the break, we saw that we could get policy iteration kind of massaged into this form where we want to maximize some objective. It's a very convenient objective because theta prime, the optimization variable, only appears in one place, here in the numerator of the importance weight. The advantage comes from the old policy, the expectations all come from the old policy, and as we remember from the policy gradient lecture, if you want to compute the derivative of this thing, all you do is you put a grad log pi in there. So it's very, very convenient. You don't need any more samples, but this objective is only good to use if pi theta prime is close to pi theta in terms of total variation divergence, which means that you need to somehow impose that constraint on it. So let's talk about that a little bit more. Let's first come up with a slightly more convenient bound. Total variation divergence is very convenient for theoretical analysis, but it's very inconvenient if you want to actually implement algorithms. It's especially inconvenient if you have continuous actions, because calculating a total variation divergence between, let's say, 2 normal distributions is quite a pain. So we'd like to use a better, more convenient notion of divergence. So before we had the notion that pi theta prime minus pi theta, you take the absolute value of that, you sum it over all the actions, and that's less than or equal to epsilon. Very nice for analysis, not so nice if you want to actually try to implement it. So the more convenient bound is this. You can actually show that total variation divergence is bounded by the square root of 1/2 times the KL divergence. I'll tell you what the KL divergence is in a second. This bound is just a textbook result. You can look it up in a textbook. And total variation divergence, KL divergence, therefore bounds the state marginal difference. So if this is greater than this, and then this goes into the epsilon, then this thing therefore bounds this thing. What is KL divergence? KL divergence is defined, perhaps somewhat cryptically, as the expectation under the first distribution, P1, of the log of the ratio between the two distributions. A little bit maybe of a cryptic definition, but it turns out that KL divergences have some very desirable properties. Of course, for discrete variables, we can calculate them just by summing over all the numbers, but for many exponential family distributions over continuous variables, there are actually convenient formulas for calculating KL divergence. So for example, the KL divergence between 2 multivariate normal distributions, like the ones we might use for continuous action policies, there's just like a formula, you look it up in a textbook and you write it out and it calculates this for you. Whereas for total variation divergence, there's no such thing. So we would prefer to use these KL divergences because many commonly used parameterizations for distributions have easy to calculate KL divergences. So we're going to use that instead of actually constraining the total variation divergence between our two policies, we'll instead constrain their KL divergence, which will be much easier to do. Okay, so now we have a slightly different objective, the same objective but a slightly different constraint, which is that the KL divergence between the policies is bounded by epsilon. And now we'll try to actually think about how we can optimize it. So one way that we can do it, which is not the way that we actually do it in policy gradient, but it's perhaps somewhat helpful to think about, is you can write out the Lagrangian of your constraint optimization problem. So when you write the Lagrangian, you just take the objective, and then you add the constraint times your Lagrange multiplier lambda, or if you prefer lambdas to be positive, you subtract it. So you have the KL minus epsilon times lambda. Okay? And you know that if you pick the right lambda, then optimizing your Lagrangian will give you the right answer. How do you pick the right lambda? You do it by optimizing the dual. We won't talk about that in too much detail. But a practical algorithm that you could consider actually implementing, and such an algorithm would in fact work, there are algorithms that do this, is to alternate between maximizing your Lagrangian with respect to theta prime and then taking a step on the dual variable, on the Lagrange multiplier. I'm going to explain the intuition behind this, and I'll actually derive this algorithm that's called dual gradient descent in a subsequent lecture. The intuition behind this is if your constraint is violated too much, meaning the KL divergence is larger than epsilon, you increase lambda. So if you're violating the constraint too much, increase the multiplier. If you are not violating the constraint, if the KL divergence is less than epsilon, then you decrease lambda. You basically downweight that term. And that's exactly what this update rule will implement. So that's the intuition. Raise lambda if your constraint is violated, lower lambda if your constraint is not violated, and hopefully this will end up with a value of lambda that will actually ensure that your constraint is obeyed. Later on, in a subsequent lecture, we'll see that we don't actually have to hope that for some functions this is in fact guaranteed. But for now, let's just go with the intuition and take my word for it. This is an instance of something called dual gradient descent. And you can actually implement an algorithm like this. This will not correspond directly to any of the policy gradient methods we've learned about so far, but it will be a viable way to set up a policy iteration method. And of course, when you do step one, you don't have to optimize that Lagrangian to convergence. Typically, if you have a deep net, you don't really want to optimize anything to convergence. So it's OK to take just a few gradient steps there, and that's still reasonable. How else can we optimize this objective? It'd be really nice if we could do this, if we could somehow like take this and reduce it to something that looks a little bit more like the policy gradient method that we've learned about. So let's call this thing A bar, just like I did before. So our objective is A bar. We have a constraint, which is that the KL is less than or equal to epsilon. One of the ways that we can approximately optimize some objective is we can take a Taylor expansion of that objective and optimize that instead. So if you have some complicated function like this, and you know that you only care about optimizing that function within some region, within that red box. So you can think of that red box as being of size epsilon. If that box is small enough, then inside of that box, a Taylor expansion of your function will probably be close enough to the original function that you could optimize the Taylor expansion instead. So you could, for example, make a linear approximation, which is denoted by that green line, and the optimum for that linear approximation might be close to the optimum for the original function if the box is small enough. So for any Lipschitz continuous function, for a small enough box, this is going to be true. So let's try that. Let's do a Taylor expansion, and let's do the simplest Taylor expansion, just a first-order Taylor expansion. So if you do a first-order Taylor expansion, your objective becomes gradient of A bar transpose theta prime minus theta, subject to the constraint that the KL divergence is less than or equal to epsilon. Now, conveniently, we already had a constraint to make it less than or equal to epsilon. Now this constraint is kind of pulling double duty. It's both making sure that we're in a small enough region that our really, really lame Taylor expansion is actually reasonable, and it's making sure that we get that guaranteed improvement. So just take the smaller of the two. OK, so far so good. We have a constraint, we have an objective. Our objective now has become much simpler. It has become, in fact, linear. But we have to calculate that gradient. It's very convenient to calculate the gradient at theta rather than at theta prime, because at theta,
the importance weight ratio becomes 1. So that gradient of A bar is exactly the policy gradient. Okay, so now we have a linear objective and we have a KL divergence constraint. We're getting to something that looks a lot more like a policy gradient. I mean, at least our objective has a policy gradient in it, but our constraint is this weird KL divergence thing. So there's our A bar, gradient of A bar. You can see the policy gradient lecture for the derivation. But if we evaluate that gradient at theta, it becomes even more convenient because your importance weights vanish. So the gradient is just grad log pi times A, which is exactly the policy gradient from before. So that's very nice. We can simplify that. And that's all the same as in the policy gradient lecture from before. All right. So now what we really want is we want to actually just do gradient ascent on this. That's what policy gradient does. And we're almost there. We have this objective with our gradient in there, times theta prime minus theta, and we have this weird constraint. So to really conclusively tie this back to policy gradient, we need a little bit of an additional tool. We need a way to understand how gradient ascent actually implements a sort of constrained optimization. So here's our policy pi theta. I'm going to come back to this bit about how some parameters change the probabilities a lot more than others. My claim is that gradient ascent implements something quite a bit like this optimization, but with a different constraint. My claim is that gradient ascent maximizes that linearized objective, subject to the constraint that the L2 distance between theta and theta prime is bounded by some number. Why is that true? Well, let's look at a picture. Let's say that this is theta, and this circle has radius epsilon. The coloring in the background shows the objective. So bluer colors are bigger, redder colors are smaller. It's a linear objective, so it's essentially like a linear gradient over this whole thing. So you want to go in the bluest direction possible, but still stay inside this circle. That's what this problem is telling you to do. So if you know that you're going to be on the edge of this circle, it's a linear objective, so the optimum is at infinity. The further you go, the better. If you know you're going to be at the edge of the circle, which point on the edge should you choose? Well, you should choose the bluest point, because that's the biggest one. Which point is the bluest one? Well, it's the one in the direction of grad J. So you just go in that direction. You go as far as you can until you hit the wall, and then you stop because you have to stop, because you have a constraint. So you know where this point is going to be. It's going to be theta plus grad J times some number. And what number is it going to be? Well, it's the number that puts you on the edge of the circle. So it's going to be theta plus grad J, and then the number in front of grad J is whatever ensures that this vector is of length epsilon. So you divide it by the norm and multiply it by epsilon. You take the square root because the constraint is on the square, and that gives you your update. Don't worry too much about this complicated square root term, because in the parlance of policy gradient, that's just your learning rate. This just says that if you actually want to enforce a constraint of epsilon, choose your learning rate like this. You can choose it some other way too. That's a heuristic, but that's OK. So gradient ascent optimizes a constraint optimization problem. It finds the best objective value for a linearized objective inside of a epsilon ball, the bluest point on the circle. OK, but this is no good. This is no good because we didn't want this kind of constraint. We wanted this kind of constraint. We wanted to constrain the KL divergence between the policies, not on the Euclidean distance between parameter vectors. Euclidean distance between parameter vectors is no good because different parameters will change the distribution by different amounts. But at least now we know what policy gradient is doing. Policy gradient is trying to do this, but failing in doing this instead. So it is a constraint optimization. You can say, well, if the parameters are really, really close, and your distribution is continuous in the parameters,
then the distribution is also close. But it's not a very good constraint because some parameters will change the distribution much more than others. So policy gradient does the job for a really, really small epsilon, but we can do the job better. All right, before I tell you how to do the job better, does anybody have any questions about this? Yes?
So what about gradient methods that change, like have different learning rates for each time?
Yeah, so what about gradient ascent or gradient descent methods that adaptively adjust the learning rate? Well, it kind of depends on how you adjust them. If you look at, for example, what Atom does, does everyone here know what Atom is? Okay, so Atom is an adaptive learning rate method, probably something you've used before or maybe are even using now. Atom adjusts your learning rate, and one of the things it does is it takes the norm of your gradient and it divides the learning rate by that. Quite similar to this. So in fact, the adaptive learning rate methods actually arguably are in many cases closer to this kind of thing than just picking the number by hand. Any other questions? All right. So far, where have we gotten to? We've tortured our constraint optimization objective by linearizing it and putting in a KL divergence and so on to get this. Then we've tortured it some more by arbitrarily replacing the KL divergence with a Euclidean distance between parameters. And from that, we got exactly our policy gradient. So we've gotten to policy gradient, but we've also learned along the way that this is perhaps not the best way to do this. So we've reached our destination and found out that it's the wrong destination to go to. Can we do better? Can we do something more like this? Can we account for the fact that different parameters will change our distribution by different amounts? So these are not the same. What we're going to do is we're going to use a Taylor expansion one more time. Before we did a Taylor expansion on the objective, now we will do a Taylor expansion on the constraint. So if you are very, very close to your previous policy, meaning the KL divergence is small, then you can approximate your KL divergence with a Taylor expansion of the KL divergence. Just like if you only move by a small amount, you can approximate the objective with a Taylor expansion. You can approximate the constraint with a Taylor expansion. And we're going to use a second order Taylor expansion this time. The second order Taylor expansion for any function that has that's 0 at the origin is just a quadratic function. And so it's no surprise that the second order Taylor expansion of a KL divergence is also a quadratic function. The interesting bit is what the matrix in that quadratic function is. This bit I'm going to just tell you, so you can look it up in a textbook or attempt to prove it on your own. But what that matrix is equal to is something called the Fisher information matrix. So the Fisher information matrix, it's going to look a little weird, but that's what it is. It's the expected value of the outer product of your gradients. This is just the definition of Fisher information matrix. And you can, in fact, show that that is the matrix that goes in there for F for the second order Taylor expansion of the KL divergence. How can we practically calculate something like this? Well, it's kind of tough because it's an expectation, but you can use samples. And conveniently, since you have to evaluate this at theta, not at theta prime, you can use the same exact samples that you already got back when you sampled theta. So the same samples that you used to estimate the objective, you can use to estimate the Fisher information matrix. And this gives you a second order Taylor expansion of your KL divergence. So now we can replace our KL divergence constraint with this much more convenient quadratic constraint. Now, when you have a quadratic constraint, the picture is exactly the same as the picture before, except that instead of a circle, you have an ellipse, right? Because you can think of this F as just rotating and rescaling everything. So it's still, you know, the previous one, the Euclidean distance, this one here, this is also quadratic. It's just quadratic where the matrix is identity. Now we've just made that matrix not be identity. So instead of a circle, we have an ellipse. But same exact thing holds. The bluer the better, land somewhere on the boundary. And then the only question is, where on the boundary do you land? Well, very simple. Ellipses are hard to deal with. So instead of trying to optimize on an ellipse, just transform your objective by F inverse. So right now you have an objective which is grad J times theta prime minus theta with a constraint which is a norm under f. You'd rather have a constraint that's a norm under identity, so just apply f inverse to the objective. So if you apply f inverse to the objective, now you're on a circle again, which means that you can find the optimum just by taking a step in the direction of the gradient, but now multiplied, of course, by f inverse. So that means that if you want to find the optimum on the ellipse, it's just theta plus some number alpha, and you have to choose that number carefully. In practice, we won't choose it carefully, but in theory, you have to, times f inverse times grad j. So all we've done is we've stuck that f inverse in there, which accounts for the fact that this is not a circle, but in fact an ellipse. If you want to know how to choose alpha, it's just a little bit of algebra. You have to make sure that this quadratic form is less than or equal to epsilon. So the way you do that is by taking the square root of 2 times epsilon divided by the squared norm of j under f. It kind of makes sense. You can sort of think of the denominator here as the squared length of grad j under the metric f. So before we had just the squared length of j, now we have the squared length of j under f. Okay, so if you use this as your alpha, and you use this gradient update, then you will obey this constraint approximately up to a second order Taylor expansion. And the only real substantive change this implies to our policy gradient algorithm is that now we multiply the gradient by f inverse instead of just doing alpha times the gradient. This is called the natural gradient. Why is it called the natural gradient? Well, because this gradient will change your distribution by the same amount regardless of how that distribution is represented. So maybe you want to parameterize your Gaussian in terms of mean and variance, or maybe for some reason you want to parameterize in terms of squared means and log variances. Reparameterizing your distribution like that will change the gradient, and it will change how much each gradient step changes your distribution, but it will, in fact, not change how much the natural gradient changes your distribution. So the natural gradient, for every step, it'll change your distribution by the same amount, regardless of how you parameterize it, which means that this issue with different parameters affecting the distribution of different amounts is compensated for by using the Fisher information matrix. So this is closer to the constraint optimization that we wanted all along. Any questions about this? Yes?
In what cases is the hyperellipsoid degenerate or near degenerate?
Yeah, so when is this thing degenerate? It can be degenerate, for example, if your f is not full rank. So you might run into some trouble there. In practice, I'll actually get to some practical tips for how to use this to not have everything crash and burn when that happens. Of course, for a giant neural net, f is going to be some enormous matrix, so the chance of it not being degenerate is actually very low. But you can use some partial CG solvers to compensate for that, and I'll discuss that later. There's a question back there?
It's kind of similar to his. If you're estimating f with sample from the expectation of essentially xx transpose, it's going to be rank 1, and then you're inverting it.
Yeah.
So how do you even make that?
Right. So the question was, well, you're you're estimating this with outer products of vectors, and those vectors come from samples. It's actually even worse, right? For a neural net, you have a million parameters, it's a million by a million. Unless you draw a million samples, you're not going to get a full rank matrix. So hold that thought, and we'll see the deep learning solution shortly. The deep learning solution, always a little bit of a hack, but tends to work well. Any other questions? Okay. All right. Is this stuff even a problem in practice? Like, it's nice that we have this kind of funny ellipsoid thing before instead of a circle. It's a little bit more interesting. We can do lots of math and get ourselves really confused. But does this actually matter? So let's talk about a little toy problem that illustrates why it matters. Because if something goes wrong even in a toy problem, it'll probably go wrong in realistic problems. Here's my toy problem. My state is somewhere on a number line, so it's one number. And my goal is to reach 0, so that's 0 right there. And here's where I am now. And I get to go left or right. In fact, I get to go left or right by continuous number. So I have one number for my state, one number for my action. And my reward is the negative
squared state value, so meaning larger values are worse, getting to 0 is what I want, and the negative squared action value. So ideally, I'd like to get to s equals 0 and take a equals 0, and that gives me the largest reward. Bigger actions incur a cost, bigger states incur a cost. Very, very, very simple reward. And my policy is going to be a normal distribution. So this is the equation for the logarithm of a normal distribution. The mean of that normal distribution is going to be some number k times the state, and the standard deviation is going to be sigma. So this policy has two parameters, k and sigma. It's not a neural net, it's just two numbers. So policy optimization consists of figuring out the best k and sigma to maximize this reward. So it's a normal distribution, which means that you kind of walk around, you're going to do a Gaussian random walk biased by this k. Okay, so this should be a very simple policy gradient problem. Now, fortunately, it has two parameters, which means that we can visualize the gradient for every parameter value. And I didn't make this picture. I borrowed it from a very nice paper by Peters and Schall, and I'll have a reference to that. The reference for this was actually in the policy gradient lecture. So the horizontal axis is k, the vertical axis is sigma. The blue arrows show the gradient. The optimal value is right there. It's a gain of -1 and a sigma of 0. So the best policy is a deterministic one. We already know that. And the best gain turns out to be -1 for this problem. The blue lines show the gradient. And for those of you that have kind of looked at pictures like this before, those blue lines should look very, very disturbing. Does anybody have any guesses as to why those blue lines should be a cause for concern? Back there, yes.
Because the blue lines end up pointing just straight downwards at the end, and don't point inwards
Yeah.
towards the -1 gain.
Mm-hmm. The blue lines don't point to the optimum. That's kind of crazy, right? It's the gradient. It should point at the optimum, but it doesn't. It actually kind of does. These blue lines are very, very, ever so slightly tilted. They're ever so slightly tilted towards -1, but very, very slightly. So this is very bad. This means that if you follow the policy gradient, you will reduce your variance very quickly, and you will probably spend all of your time reducing your variance instead of actually going to the optimal k. And it's actually the k that determines what your mean is. So that's really important. This is essentially the same problem as the ill-conditioned optimization problem you might imagine if you optimize a quadratic function with a matrix that has a really large condition number. So if you have kind of an ellipsoid-shaped function like this that you're optimizing, maybe your gradient will zigzag back and forth and take a really, really long time to get to the optimum. And the more stretched out this ellipsoid is, the more gradient steps you'll need to reach the optimum, because you'll spend all your time zigzagging instead of actually going straight to the goal. So this is a very ill-conditioned optimization problem. But it's not a pathological problem. It's actually a very, very simple, very logical policy for a very, very simple reinforcement learning problem. So this is very bad, and we use these normal distributions all the time. So we should be very worried about this. The natural gradient is shown with these red lines on the right here. And it's actually fairly easy to derive the natural gradient. In fact, for a normal distribution, you could actually calculate the expected value of those grad log pi's analytically, which is very nice. The natural gradient looks much, much better. In fact, the natural gradient will get you to that -1, and then it will crunch down the variance, which is exactly what you'd want. They're both gradients. They both point in an improvement direction. It's just that this improvement direction is much better, meaning that you will get to the optimum with many fewer steps. Does anybody have any questions about this illustration? Okay. All right. So some notes about practical methods, and this is where the ill conditioning stuff will come in. So natural policy gradient. The natural policy gradient refers to the case when you do theta prime equals theta plus alpha f inverse grad j. F inverse f is estimated using samples. There's a little bit of a numerical trick for computing f inverse times j that I'll mention in a second. Generally, this is a good choice to stabilize policy gradient training.
It will allow you to get better policies in fewer steps, and it's particularly useful if you have things like Gaussian distributions in your policies. If you want to learn more about that, check out this paper, Peters and Schall, Reinforcement Learning of Motor Skills with Policy Gradient, which is where I got these pictures. A practical implementation of this method requires efficient matrix vector products between the Fisher information matrix and a vector. It's a bit non-trivial to do this without computing the full Fisher information matrix. Why don't we want to compute the full Fisher information matrix? Well, because if you have a neural net, you have 1,000,000 parameters. That's a 1,000,000 by 1,000,000 matrix. In practice, you never build that full matrix. In practice, there is a trick to calculating F inverse grad J by repeatedly calculating F times grad J using the conjugate gradient algorithm. This is described in this paper, Trust Region Policy Optimization. So in the appendix of this paper, there's a full recipe for a numerical method based on conjugate gradient that doesn't have to solve a linear system of equations like this explicitly. It doesn't even have to build F explicitly. It just repeatedly calculates F times grad J and never actually builds the full F either. And that's how you want to do it if you have a neural net. Otherwise, this is going to take forever. So Trust Region Policy Optimization, basically the same thing as that, only where you choose alpha using the rule that I had before. So natural policy gradient, you choose alpha yourself. Trust Region Policy Optimization, you choose epsilon yourself, and you calculate alpha using this rule, which ensures that your KL divergence, at least according to that Taylor expansion, changes by a fixed amount every step. So you can think of this as an adaptive step size adjustment, kind of a fancier version of Adam specialized to natural gradient. You could also just use the importance sampled objective directly. So instead of doing policy gradient as I've described, you could do the dual gradient descent version from before, where you write out that full A bar objective, you have the constraint, you have a Lagrange multiplier, and you actually adjust the Lagrange multiplier. So it's sort of a regularizer that keeps you close to the old policy. And there are methods that do that also. So if you want to check that out, look up proximal policy optimization. So these are kind of the three main classes of policy gradient style methods that use this policy iteration connection and in practice can work a lot better than the vanilla policy gradient that you guys are doing for homework 2. Okay, so to review, we learned about how policy gradient is policy iteration. We can optimize the advantage under new policy's state distribution, and that's perfectly correct, but of course intractable. So you use the old policy state distribution, which optimizes a bound if the policies are close enough. This results in a constrained optimization problem. A first-order approximation to the objective gives you gradient ascent. Regular gradient ascent has the wrong constraint, so you use the natural gradient if you want an approximation to the right constraint. And some practical algorithms derived from this are natural policy gradient, trust region policy optimization, and proximal policy optimization. Okay, so that's it, and I'll see you all on Wednesday for model-based RL.